In this video, we're going to be talking about something called a finite state machine, which is a very useful structure for thinking about designing firmware for embedded systems and for mechatronic systems. And we're going to show walk through a couple of different ways of coding up a finite state machine. And just to remind you of what's connected here to my Arduino, in case you skipped the blinking LED series of videos. Here I have 3 LEDs, which we're going to make use of in this finite state machine. I've got a green LED connected to pin D13. We've got a yellow LED connected to pin D12, and we've got a red LED connected to pin D11. And these are in series with a 200 ohm current limiting resistor in each case. And we've got 2 tactile switches. The switch pulls high. The 2 different inputs, D10 is connected to switch 1 and D9 is connected to switch 2. And so when we push the tactile switch, that pin is going to go high. And then we've got a 10 kilo ohm pull down resistor that's going to be responsible for restoring the voltage on the digital inputs back low once the switch lets go. So we also have the pot here connected to A0, but we're not going to make use of the pot in this particular example. And so a finite state machine is a system, a computing system, that has a certain finite number of different discrete modes of operation or states that it can be in. And you'll make a transition from one state to another when certain events take place. And we usually represent the sort of state transition behavior for one of these things as a graph. And so here I'm going to represent the behavior of my simple state machine example here with 3 circles. So the nodes in the graph represent the different states, and we're going to call this one red. We're going to call this one yellow. I'm sorry, this one is green. This one's going to be green, yellow, and red. And the behavior in the green state is going to be very simple. The green LED is going to be on steadily in the green state. In the red state, the behavior is also going to be very simple. The red LED will be on constantly in the red state. The yellow state is a little bit more interesting. In the yellow state, the yellow LED is going to be flashing at 1 hertz. So it'll be on for 500 milliseconds and off for 500 milliseconds. Tremendously interesting. And so what we do is we represent a state transition by a directed edge in the graph. And so in this particular case, we're going to be able to go from the green state to the yellow state. And we label the edge with the event, or with something that denotes the event that will initiate the state transition. So we're going to say switch 1 high. So when we push switch 1 goes high, and if we're in the green state, that will initiate a transition to the yellow state. If we're in the yellow state, we can get back to the green state by pressing switch 2. Also in the yellow state, we're going to be able to make a transition to the red state after 10 seconds. Have passed. And that's going to be equal to or equivalent to 20 toggles of the LED. And once we're in the red state, we stay in the red state. There is no getting out of the red state. So there are many different interpretations that you might be able to give to a system like this. One which is a little on the ominous side would be that this is kind of like a simple bomb with the green state being kind of a ready state, and when we push switch 1, we arm the bomb and there's a 10-second fuse, and then we enter the red state, and that is boom. And there's no getting out of the red state. But once we're in the countdown phase, we can go back to the ready state and disarm the bomb. There are probably less ominous interpretations or stories you could tell to go along with this. I'll leave that to your devising if you care to. But I have this state machine running, and so we can see what it does. If I push switch 1, you can see I'm going into the yellow state. And if I'm in the yellow state, I can push switch 2 and get back into the green state. If I wait for 10 on-off cycles to occur, I go from the yellow state into the red state. And I can push these buttons all I want to, and I don't get out of the red state. Now I can, of course, reset the Arduino by pushing this little reset switch here, and after a few flashes I get back into the code, and I run the code again, and I'm in the green state, switch to the yellow state, switch back to the green state, switch back to the yellow state, and then if I wait long enough I go back to the red state. So how does this code work? Well, here we have our blink interval, just like we had in the blink LED, blink millis sequence of programs. We have 3 different pins, one for the green LED, one for the yellow LED, one for the red LED. We've got 2 pins defined for the tactile switches. Here we have something called an enumerated type, which is going to be basically an integer variable that can take on a certain finite number of values, which are named. Here, these are going to be the value that represents the different states our finite state machine can be in. We have the green state, the yellow state, and the red state. And by default, I believe green will have the value of 0, yellow will have the value of 1, and red would have the value of 2, but we never really need to know exactly what those values are, because we're going to be testing against green, yellow, and red, instead of actual numbers like 0, 1, and 2. And so this enumerated type we're defining has the name states, and so we're going to make a variable called state, which holds the current state of our finite state machine, and it is of type states. And then for the behavior in the yellow state, we're going to have 2 global variables. One remembers the time at which the yellow LED last changed state, and then we have a 16-bit unsigned integer, which is going to keep track of the number of times that we've toggled the yellow LED. And so our setup function initializes the 3 LED pins to be outputs, the 2 tactile switch pins to be inputs, and then we're going to set the green LED high initially because we're going to be in the green state, and that's what happens in the green state. So we set that high initially, we set the yellow and red LEDs low, and we set the initial state of our state machine to be green. And then inside the event loop, or the loop body, we're going to be doing a switch statement here. We're going to look at the value of state, and in the case that the value is green, we're going to do this block of code. In the case that it's yellow, we're going to do this block of code. And in the case of red, we're going to do this very simple empty block of code, because there's no getting out of the red state, and nothing happens in the red state. So if we're in the green state, we're going to basically check to see the value of switch 1 is high, and if it is, then we have to initiate a transition to the yellow state. And so some things have to happen in that case. We're going to have to set the green LED to low and make the state assume the value of yellow. Then we're going to turn on the yellow LED, and we have to remember the time at which that happened. And then we have to initialize the yellow count value to 0. And then we'll be all set up to get into the yellow state. Now, if we are in the yellow state, we've got a little bit more work to do. We have to keep track of the animation of the LED. So we have to check to see if it's time to toggle the yellow LED. And if it is, we toggle the yellow LED. Remember that time is the new yellow time. And then we have to bump up the yellow count. So this is very similar to what we did in our blink millis sketches. And then we start checking for the state transitions. So in the yellow state, if switch 2 is high, then we want to go back into the green state. So to do that, we have to turn the yellow LED off, change the state to green, and then we have to turn the green LED on. If we're not doing that, then we check to see if yellow count is equal to 20, which means that 10 seconds have passed, and that'll be time to enter the red state. So we have to turn the yellow LED off, change the state value to red, and then turn the red LED on, and then we're set up to go into the red state. Now, this way of coding the state machine works. It implements the behavior that we described and that we intended, but it's not particularly great code. For one thing, we've got all of these cases all in one ginormous switch statement. Now this isn't really huge, it fits on one page, but you can imagine that if we had many more states, or the behavior in each state was much more complicated, then this could get to be a very long switch statement. And we have these sort of if statements inside of the switch statement, and that's not great. The other problem with this code is that we've got stuff pertaining to the yellow state in the green state. We've got stuff pertaining to the green state in the yellow state block. And we've got stuff pertaining to the red state in the yellow state block. And that's really not very maintainable. You could imagine that if multiple states, if you can enter a state from multiple states, then you've got the initialization code for that state in multiple places. So you've got redundancy because you've got extra copies of the initialization code, and if you were to have to change that, you would have to find all of the different places in the code where you do that same behavior. And so that just makes the code very, very unmaintainable and not very clean. And so for a very simple state machine, you can probably get away with this, but it's not super good practice to do so. So I want to show you a second version of this, which is basically a reorganization of this code into something which is much cleaner and much more maintainable. I didn't want to do that. I want to lower this. And where do I find my other one? There we go. I didn't want to make that big. I want to make that there. Okay, so here we have the same basic constants as we had in the first version. Here we're adding a fourth value of none to our enumerated data type, and that's going to represent not one of the actual states, but it'll represent sort of like a null state for us. And you'll see why that is in just a minute here. And so we have now two variables of type state. One encodes the current state, just like it did before, and we're going to also remember the prior state, like the last state that we were in. And now instead of having one giant switch statement, we're going to break up the behavior of each of the states into separate functions. And if these were complicated, we might even put them in separate source files. But we're going to call the state handler function for the green state green. We're going to call the one for the yellow state yellow. And we're going to call the red one red, strangely enough. And these are going to be simple functions that don't return any values and don't have any parameters. And so what we're going to do is when we first enter the state handler function, we're going to check to see if the value of the current state is different than or different from the value of the prior state. If they are out of sync with each other, that's going to be an indication to us that we just made a state transition. And we're calling the state handler for the first time since we made that transition. And what we're going to do here is we're going to basically put the initialization code that handles what happens when we enter a state here. And so this happens only once in the code, and that's going to be very nice. So if we see a discrepancy between state and prior state, then we make prior state the same as state, so that the next time we enter this code, we will not enter the body of this if statement. And here our initialization code for the green state is to turn the green LED on by setting green LED high. After we've done the initialization, if necessary, then we have a place to put code that performs state tasks. In the case of the green LED, there's no ongoing tasks that need to be performed. And then we have code that checks for state transitions. And here we only have one state transition, and if switch 1 is high, then we want to change the state to yellow. But we don't need to do the stuff to clean up the green state, to exit the green state, or the initialization stuff to go into the yellow state. So this is very, very nice, very clean. So if we're going to make a state transition, all we do is we change the value of the state variable to the new value, to the next state. And then the last thing we do before we leave the state handler function is we again check for a discrepancy between state and prior state. So the only way that that will happen is if we've made a state transition. And that'll be our signal to do any cleanup tasks that need to be done when we leave a state. And so in this case, for the green state, we need to turn the green LED off when we leave the state. And so by using this sort of state not equal to prior state check at the beginning and the end, we can actually very nicely encapsulate all of the behavior associated with the green state in the green state handler function and not have duplicate code running around in other states that pertains to this state. So that's a very nice way of partitioning the code into separate chunks that make it very maintainable. So all the stuff that pertains to the green state is in this green state handler function. So the yellow state handler function is going to have a very similar structure. It'll be more interesting in this case because the yellow state is a more complicated and more interesting state. So if in the yellow state handler function, if we find that state is not the same as prior state, then we sync up prior state to the same value as state, and we turn the yellow LED on, remember that time, and set the yellow count to 0. So this was the initialization code that we needed to do when we entered the yellow state. But now it's here in one place only. So our state tasks for the yellow state are to check the time and to see if it's time to toggle the yellow LED. And if it is, we do so and we bump up the yellow count. State transitions. Okay, so if switch 2 is high, we change the state to green. Else if yellow count is 20, then we change the state to red. And so again, this is just changing the state variable to a new value. And then on exit, we check to see if we've made a state transition up here somewhere, and if so, then we turn the yellow LED off. And that's all there is to the yellow state function. Now the red LED state or state handler function has the initialization part that turns the red LED on. There's no state tasks, there's no state transitions, and here I have included an exit condition here that turns the red LED off, and that I figured this would be useful in case we ever wanted to add to this state machine and make a transition out of the red state. We would already have that that code here in place. There's no chance that this code will ever be executed in the case of the red LED or in the case of the red state as the state machine stands. So you could comment this out if you wanted to, but I generally I guess I would probably keep it in myself, but that would be up to you. So our initialization is a little bit different in this case, or a setup function sets up configures the output and the input pins, but in this case we're setting all of the yellow red, green, and yellow LEDs to low instead of setting the green one high, because we're going to set the green one high when we first enter the green state handler function for the first time. So this is all uniform now, instead of having a special one that we deal with separately. And then we have to initialize prior state to a value that's different than the initial state, so that we will execute the initialization code for the green state when we first enter that. So here I've used that value of none because there hasn't been a prior state yet when we first are starting up. So that seemed to make sense to me. And then I set the initial state to green, and that's it. Our loop function is a very simple switch statement that basically just, in the green case, calls the green state handler, and the yellow state calls the yellow state handler, and the red state calls the red state handler. And so that is a very clean, very short loop function. And this code is much cleaner, much more maintainable than the original code. So it looks a little bit longer, but that's because we've added some comments and because we've kind of added these new functions here. So, but anyway, this is a very nice way of coding up a finite state machine. So if I push this out, it'll behave the same way as the original code did. Now we're in the green state. Now we're in the yellow state. We can go back to the green state. We can wait the 10 seconds and transition into the red state. And there you have it. So that's it for now. Thanks for watching.